Okay. Yeah. Good morning to all of you. In the previous class, we started discussing cyclic code. So cyclic code, first of all, is a linear code. Then afterwards, um, so right shift up. Generally, we'll confine to right shift only. If x naught, x1 up to xn minus 1 is a code, then the right shift up, that is x minus 1, x0, x1 up to xn minus 2 is also a code word, right? So this is what the definition is, correct? So now, so we gave some examples. Only zero code word, a code only containing zero code word, that is called a no information code, that is a cyclic code. N comma 1, that is called repetition code. Repetition code, you know that it contains only repetitions, A, like that. If I do cyclic shift, first of all, it is a linear code, and cyclic shift is also a code word. Any cyclic shift of code word is again a code word. So it is also a cyclic code. So single parity check code, right? And these are all examples, easy to check that they are cyclic codes. Yeah. And n comma n code, that means length is n and dimension is also n, correct? So that is also, that is because all the vectors are there, so it is automatically cyclic code. And we saw one more example at 7 comma 3 Hamming code, right? So this is also cyclic code, and we checked with all the examples, right? And I asked you to check this one also cyclic code. Yeah. Any Amya, is it a question? Cyclic code definition is clear? No, Amya? Okay. So I asked you to check these are cyclic codes or not, correct? Somebody can see the last one and check whether it's cyclic code or not. Mehak, are you here, right?
Yes, sir.
Yeah. Can you say that, for example, how do I check it is cyclic code or not? Correct.
So if I consider one of the codes such as 2 and 0, and if I
Uh,
do the right shift, then it
uh,
will be 0 to 1, which is available in the code.
yeah. And again, you do this one again, right shift, that 102, that is also available here. Now, if I do again this one, then 201, 210, but it's already there. Now 201, right? 012. So 201, if I shift it 120, that is available here. उसको shift करते तो 012, that is available here. 222, okay. So all cyclic shifts are here, but first of all, is it a linear code? That also we need to check, right? So if we add any of them, it should be again an element. And before that, how many elements are there? First check that, because you know that so there are total how many vectors will be there? Total. It is f3 power 3, right? F3 power 3. F3 has 3 vectors. F3 means 0, 1, 2. Now each element has 3 choices. So 3 into 3 into 3, 27. But here how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, so cyclic, first of all, linear code is a subspace. Subspace means the dimension is also 3 square or 3 power 1 or 3 cube. 3 square. That is also satisfied. But still we need to check. Yeah. Anyhow, so like that. So then we noticed that cyclic code we convert into, so you take any code word, now we can convert it into a polynomial, and we can think this as an element in fq of x quotienting with x power n minus 1, right? So cyclic shift is nothing but, so now an minus 1 comes here and a0x will come. So that is actually multiplying it by x, but with modulo x power n minus 1. So because of that, what happens? Cyclic codes are uh, so cyclic codes are comes like this, right? Yeah. So we can think of cyclic code as an element in fq of x quotient with x power n minus 1. So Amya, are you here?
Yes, sir.
Yeah. So actually what happens is that we saw that one-to-one correspondence between, see, even whether it is not cyclic code also, this is possible. Fq power n is what? Is a vector space over fq of dimension n. Fq of x quotienting with x power n minus 1 is also vector space of a vector space over fq of dimension n. So there is a one-to-one correspondence, converting it into a polynomial. But cyclic code has extra property. Not only just it is like this. If this is there, then its shift also will be there. Shift is there means what? So multiplying it by x, then a naught, a1 x square, and so on, an minus 1 x power n. But x power n is 1. If I do modulo x power n minus, that means an minus 1 comes here. That is the beauty here. Okay. So then we noticed that what we proved in the previous class is that C is cyclic code if and only if Cx is an ideal. What is the C? C is a subset of fq power n. What is Cx? Corresponding polynomials. Is it okay, Amir?
Ideal in the quotient ring, right?
Ideal in quotient ring, yes. So this is a beautiful thing. So cyclic codes are actually subspace of fq power n. But now I associated each polynomial to what? I associated each polynomial to sorry, each code word to polynomial, right? But quotient with x power n minus 1. So what we proved in this part is that if C is a cyclic code, then associated polynomials together, they form an ideal here in fq of x by x power n minus 1. Yeah, this we proved yesterday. Proof is not complicated. Yeah. And what do you know about fq of x as a ring theory point of view? Fq is a field. What do you know about fq of x?
So PID.
PID, right? It is a principal ideal domain. Even quotient also PID. But even then I proved here in the next class. That is what I want to tell you. So even if you miss, it is not a problem. If C is, see, now onwards, actually there is no difference between C and Cx. Yeah. So C is actually subset entuples, but you know that polynomials and entuples are we can associate. But cyclic code extra thing is that quotienting with x power n minus 1 also. So C is cyclic code. So now Cx is an ideal we proved in the previous theorem, right? But this ideal is generated by single element, generated by yeah, it is a ideal, a principal ideal. So now, as you know, ideals are generated by many elements, but Gx is the monic polynomial of smallest degree, then that is the generator. So Gx is unique and every code word is a multiple of Gx because it's a proof is given here. Actually, instead of because we are not discussed ring theory before, those who are already know fq of x is PID, then quotient also PID, then no need to do this theorem. This is just that. We actually proved it by using division algorithm. Right? Is it okay, Amir?
Yes.
What is it we are telling? Now this theorem says that if C is a cyclic code, then the Gx, the minimal monic polynomial of smallest degree is the generator. And every code word is a multiple of Gx. Right? This is what we done. Okay, just recalling. So the monic polynomial of smallest degree is called generator polynomial, like generator matrix. Yeah. Then we proved another thing that generator polynomial of cyclic code divides x power n minus 1, and every divisor of x power n minus 1 is generator polynomial of the cyclic code. That means there is a one-to-one correspondence between divisor of x power n minus 1 and the generator polynomial. Okay, this is what we established in the previous class. So for example, I want to find all cyclic codes in f2 power 3, right? f2 power 3 means uh, code words of length 3, right? Code words have length 3. Now we need to find all cyclic codes here, right? So that is equivalent to say that I'll first split x cube minus 1. It is x plus 1 into x square plus x plus 1. right? Now, what are the divisors of this polynomial? Is x plus 1 and x square plus x 1, x plus 1, x square plus x plus 1, x cube plus 1, right? Okay. By the way, one point here I want to mention. See, what is that we are saying here, right? Okay, 1 minute दीजिएगा. So I'll just do one thing. Right, give me 1 minute. Yeah. Yeah, I have to open this one actually. Yeah. Okay. Right. So oh, some problem is coming. Okay. So yeah. So one point I want to mention here is that every divisor of x power n minus generates a polynomial cyclic code, and in the previous result we showed that.
Sir, something is blocking.
Okay, that is okay. Yeah. So gx is so every code word is a multiple of gx that we mentioned in this theorem, right? We proved in the previous class. So that I'm using here. So what is that I want to convey is that, for example, my polynomial gx is the generator polynomial, right? What is actually my c of x or c code words are exactly. So every code word, so code word is a polynomial again here, right? So code word belong to c means it is divisible by gx, right? So then what is at my c actually? My c is some a of x into g of x, right? G of x degree is how much? N minus k. Yeah, degree of gx is n minus k, and the code word length is n. Right? So ax is a polynomial of degree at most k minus 1. Why k minus 1? Because if I multiply them, then the degree product of entire polynomial degree is at most n minus 1, right? So that is exactly by quotienting by x power n minus 1 means, right? But what is ax now? Ax is any polynomial now. I am free to choose. It is like, when you have a this matrix k cross n. Here I can multiply with any any vector of length k, right? The resulting is the code words, correct? Similarly here, but you can ask me why I told polynomial of degree k minus 1. Degree k minus 1 means it contains k terms, right? So a of x equal to a naught plus up to a k minus 1 x power k minus 1. So this is belong to fq of x, right? So now I am not quotienting as such. See, multiply, if I multiply, I will get polynomial of degree less than n, right? So is it okay? This part is okay. So what is the dimension then now? It is equal to how many polynomials are possible, ax, right? So that is exactly fq power k. Is it okay or not okay? If you tell me, I can explain further. Okay.
Sir,
Not
but
clear?
I just have a doubt here.
Hmm.
So, if we just drop the condition on the degree of ax
Hmm.
and take any polynomial in fqx, and then quotient it with x power n minus 1. Then it will be the same thing, right?
It will be the same thing, but actually that they are again equivalence classes, right? The equivalence class of these one, they are going to be one of the equivalence class of these polynomials only.
Yes, sir. But
Yeah, so now I'm completely free. I'm thinking that I'm not working in a x power cube, x power quotienting and all. Now I'm not bringing to. Now life becomes easy. Okay, so let me see one example. Then we'll again come to your question also, right? So for example, this one plus x square, 1 plus x. Let us take 1 plus x, right? Okay. So now what is the code word length here? F2 power 3 I'm looking. F2 power 3 means code word lengths are 3, right? Now 1 plus x. Now I'm quotienting with x cube minus 1. Remember, when I quotient with x cube minus 1, then what is that? What is that f cube of x looks like? F cube of x quotienting with x cube minus 1. What is this contains? What is this set contains?
some set of all quadratic polynomials.
Quadratic polynomials, correct? Yeah, it's set of all quadratic. But now I'm telling C is this is set of all quadratic polynomials. That means, that means that one into any polynomial of degree 2. One is just one, right? This is, you understand, that is set of all quadratic polynomials, right? So what are set of all quadratic polynomials? They look like a naught plus a1x plus a2x square. Now a naught, a1, a2, I can take any scalars, 0, 0 r1, a1, 0 r1, a2, 0 r1. That is what I'm telling here. When my generating polynomial is 1, right, then my cyclic code becomes entire f2 power 3. Yeah. So that is all the words. So I'm coming back to that. Now, when my gx equal to 1 plus x, I'm explaining here. Now, what is this one? Now I'm not collecting all quadratic polynomials. I'm collecting quadratic polynomials which are divisible by 1 plus x. That means now 1 plus x I put here. Now I'll multiply with a naught plus a1x. Yeah, such that these a naught comma a1 belong to f2. Now what are the polynomials I can multiply to 1 plus x, right?
Understood.
Yeah, okay. So
But so
you
my question is that
that's what I'm telling you. You are telling that instead of multiplying by linear polynomial, I can multiply with any polynomial and I quotient it, right?
no, sir. My other question was that suppose I give you some quadratic polynomial,
Uh,
then how can you be sure that we can find some linear polynomial that when you multiply with 1 plus x, you get that polynomial?
yeah, that is actually so. That is actually, you are asking like that. See, when we are working in Z modulo n, it is sufficient to work from 0 to n minus 1, right? Right.
Yes, sir.
Yeah. So that is, I know, if I multiply with anything, then it is equivalence classes actually, right? It is in one of the equivalence class. If I take any number greater than n, then it is one of the equivalence classes. Similarly, here also happens.
So, for example, like the earlier one where we took ax and gx,
Hmm.
and then we know that ax into gx will be polynomial of at most n minus 1 degree.
Yes, correct.
But how can we be sure that if I give you any n minus 1 degree polynomial,
Hmm.
you can find a degree n minus k polynomial such that ax into gx is equal to that
Yeah,
polynomial?
that is what exactly I am also saying. So exactly Jadan पे कैसे काम करेंगे, यहाँ भी करेंगे. So that you need to check. That is easy, not complicated. Okay. So you take any polynomial, multiply with now you are quotient with x cube minus 1, right? Yeah, but in order to convince you, I have to do one example. I will try to do that before. closing the class. Yeah, these are all the distinct polynomials. So let us work out this example at least now. Okay, that one only. Okay. So let us take 1 plus x, right? Yeah. So 1 plus x.
Okay, so
Now
for example, in
that
this,
is what I'm doing now here. And for this example, you can tell. Okay. Yeah. For this example, we'll do that. What is that I'm claiming? What is that you are saying? I'm saying explain you one more time to everyone. So here a of x into 1 plus x. So you are telling a of x I can take anywhere fq of x, but afterwards I will quotient with yeah quotient with x power 3 minus 1. You are telling that. Okay. I'm telling that no need to do that. Take f ax into 1 plus x, but ax degree is ax is of the form a plus bx. I not now I need not quotient, right? These are the two things. Am I correct now?
yes, sir.
Yeah, correct. So, uh, so that is obvious. Means actually, I'm not. I do not know why you are asking that question. But anyhow, what is that? Maybe something else may be there. See, here I can take any polynomial, and here you are also take any polynomial, but quotient with x cube minus 1. Once you quotient with x cube minus 1, then I cannot get a polynomial of degree 2 or more. Here, I'm multiplying with a linear polynomial with this polynomial. Again, I'll get at most degree 2 only. Okay. Now, why these two are equal? That is a question. But for that, first work out few examples. Now, a plus ax. Okay. What are the choices for ax? So here, in my case, ax can be 1, ax can be x, ax can be x square, right? Ax can be 1 plus x, ax can be 1 plus x square. Are there any other polynomials, please?
This is for the above thing, right?
No, no, I'm doing for here, for my case.
Then we only want linear polynomials, right?
Linear polynomial. Sorry. Yeah. So then I should no need to take this. You are correct. Sorry. Galat hua tha. Yes. So then I have only three polynomials or any other thing is there?
No, sir.
These three, correct?
Sir.
Yeah. These three polynomials. Why these three? Because no, there is some problem is coming.
Zero will obviously be
Zero.
zero.
Zero. Yes. Yeah. Yeah. So now if you multiply them, right? What are the possibilities? Correct. So look at them. So 0 polynomial will come. 1 into 1 plus x, 1 plus x will come. So x square plus x will come. 1 plus x into 1 plus x is 1 plus x square plus 2x. But modulo 2, so it is 1 plus x square only. 1 plus x square and 1 plus x whole square are same, modulo 2. These are the four polynomials, right? Okay. Now you take any polynomial, right? So for example, I take x square plus 1, x square plus x plus 1. Let us work out some complicated example and we'll check it. Yeah, multiply with 1 plus x. What is this going to be? This is quite obvious. This is equal to x cube minus 1. Do you agree?
Yes, sir.
But if a quotient with this one, what is I'm going to get?
Zero.
Quotient with this 0. Yes. Right? So we'll get this. Right? So like that, you take any higher, you quotient, then it is going to be one of them. Like um, uh, so you so now don't worry about I multiplied with 1 plus x or something. So I'm actually now taking this product and doing that. Yeah. So if you work out and if still problems, I can go ahead. I'll discuss later.
I understood, but I think it requires proof
Yeah.
because like the sets that we have written here, the
Hmm.
two sets that we have written. So
Hmm.
I'm not sure if it's immediately clear that these two sets are equal.
Okay. Yeah. Okay. That you can check, right? but they are equal. Okay, that is what I'm saying. Yeah. So here you multiply anything and quotient with that, and here you are multiplying only with x, and now I have no restriction. A and B can be anything, but here every time multiply and quotient with that. So now you are also observed that these are the four polynomials you get, right? And these are the four polynomials you get. And then these, what are the codes corresponding to this? 0 means 0, 0, 0. 1 plus x means 1, 1, 0. Yeah, x plus x square means.
Okay, yes, yes, sir, I understood. I proved it. So.
Yeah, that's right. That's okay. Yeah, so so these are the things. Okay. Yeah. So this is it a cyclic code? Yes, right. You can check that all of the cyclic shifts are there. Right? Yeah. So this is the thing. Now I gave one more example here, right? I'm giving one more example. So is anyone has any doubts now? Cyclic codes definition and this example. I can give one more example now. So basically, how many cyclic codes are possible for f2 power 3? Number of divisors of 4. So number of divisors of x cube minus. It is like a tau function. Okay, many times what we will do, we will take this x power n minus 1, n value, such that it is co-prime with what are the field we are working. So it is fq, right? Fq n comma q gcd1, 3 comma 2 gcd1, so that all these polynomials, all of them are distinct roots will be there, means repeated roots will not be there, right? And in fact, one more way to look at this part is that those who attended before class, they know cyclotomic cosets. Yeah, we know that x power n minus 1 is a product of some polynomials, right? How many polynomials will come? You remember? Equal to the number of irreducible polynomials, number of irreducible factors of x power n minus 1 is equal to number of cyclotomic cosets. Do you remember that?
Yes, sir.
Yeah. So now once I find the number of cyclotomic cosets, then number of divisors, number of generator polynomials are going to be, for example, this is a m. Then 2 power m cyclic codes will be passed. What is this m? M is the number of cyclotomic cosets. So what is the relation between m and n now? M divides n also. Yeah. So sorry, m may not divide n. Sorry, but this is the number of cyclotomic cosets. Yeah. This many number of sorry, this many number of divisors are possible for this x power n minus. Number of reducible factors are m. You know that is square free number, right? If I take my n is equal to 60, 30, right? 2 into 3 into 5. How many divisors are there? You know that 1 into 1, 1. So 1 plus 1 into tau function, right? You know that. So that many divisors are there. But here, the problem is that here I give a number, you will factor it and we will figure out. Of course, that is also complicated. Even for here, small values of n, how do you find the factors? That is, you simply find the cyclotomic factors. How do you find them? So n comma q gcd1, I'm working in fq of x, right? Now I have to factor x power n minus 1. What is that you do? You remember that? Okay, so again recall that. What is happening is that I'll explain you that actually. One time I will tell you, some of you may follow what I'm going to say. Others you can ask later or now, right? But it is my duty to tell that particular thing. Why we discussed those cyclotomic cosets earlier will be clear with that. See, n comma q GCD1. So I take a field FQ. Right? Now I want to factor. Now I will take FQ of X. Yeah. Now I will want to factor X power n minus 1 here. Right? Okay. Now you know that so that means it is a product of irreducible polynomials, right? You know that irreducible polynomials are factors of x power q power m minus x. Do you remember this? But here, so what are the polynomials will come? What about their degrees? Do you remember that? So you forgot what to do.
We
What
take
I
the
want- So what is it I want to say that? So FQ.
and find the generator and then take the prime powers.
Okay,
And
we'll go. I'll just give me 1 minute. So what is it I want to say that? So let us work for smaller case. Actually, Q is a prime power. Now we will get a little more complicated if I say all these things. So see, my P is a prime number, let us say. Right? Then every finite field has how many elements? So some P power n, right? So there is a finite field with P power n elements, right? We denote that field by Fp power n. But what do you know about Fp power n? Fp power m is exactly the roots of it is a um, uh, splitting field for some polynomial. Which polynomial?
x power p power n minus
X
x.
power p power m minus x, right? So actually this can be work for any prime power also, but I'm just x power p power m minus x. And we proved one thing that all these products here are have some degree. That degree divides this m, right? Okay. Now, uh, now, but these are also irreducible. These are also irreducible, right? So now what I do, this is I can write as x power p minus x power pm minus 1, right? P power m minus 1 into x. I can write like this. So here x will be there. Okay. Now this polynomial, and we proved one thing also. X power a minus 1 divides x power b minus 1 if, remember that?
A divides b.
A divides b, if and only, right? So now here I know the factors, right? These are the factors of all irreducible factors will come. Now my n divides this quantity p power n minus 1. I'm done. I'll get here. Okay. My n divides this, then so that is possible. That is possible. So what is that I want to say that for every prime p, when n comma p GCD is 1, there exists an m such that this x power n minus 1, n divides this p power m minus 1. Okay, by, yeah. So this x power n minus 1 divides this. But this is actually product of irreducible polynomials. So these irreducible polynomials of this comes from here with some factors, right? And this has a now um, this one is a finite field, so it has a generator, say alpha, right? Now this actually, you know that in the this is the way we discuss, just I'm telling. In this bigger field, this completely splits, right? x into x minus alpha into x minus alpha square and so on. I'm just recalling one more time. X power alpha power whatever, right? P power m minus 2. Am I correct?
Yes, sir.
Minus 1, sorry, minus 1. Oh, x minus 1 also there, right? X minus alpha power 0 also will come. Yeah, this is the thing, right? But now what happens? This is splitting in the big in here, but in FPP it is not like this. So this one and some other terms multiplied, and that becomes the minimal polynomial of alpha I get. Now one that is exhausted, I will take other things like that. Those are the cyclotomic cosets, right? Yeah. How do you get the cyclotomic cosets? So you denote the cyclotomic cosets as CS. You remember this is S times so Q power. So like that P power J, like that we define. Okay. Yeah. So I request you to go through them. That is the idea. So it is very interesting, provided you follow. Means you review once, because otherwise now I can tell you here without cyclotomic cosets and all, but it will be benefit. You will understand more and more that why people are working in cyclotomic cyclic codes will be much easy. Okay, sorry for this deviation a bit. Now I'm coming to the understanding of these things, simple things, so that it will not create any problems to you. Okay. One more example, x power 7 minus 1, that is x power 7 plus 1, but in F2 minus plus R. It is x plus 1 and x cube plus, so this is there. There are 3 irreducible factors. So hence we have 8 cyclic codes, right? Now if g of x, now g of x belongs to these polynomials, right? If g of x equal to 1, what is that? I'm going to get entire f2 power n, f2 power 7, right? I can multiply any polynomial of degree 6 will work. If I take my g of x equal to entire x power 7 minus 1, it generates only 0 code. This is also cyclic code. I took 2 examples, extra examples, x plus 1 and x cube plus x plus 1. Its degree is 4, right? Then what are the polynomials I can multiply to it? Degree 3. So that's why I'll get 8 codes, 8 code words. Now this is degree 6. So I can multiply only with degree 1. Degree 1 are either yeah. So yeah. So I can multiply with 0 or what is it I'm telling? So degree at most 0. At most 0. See, 6 is there. Already its degree is 6. Now a of x has to be constant. So a of x either 0 or 1. Right? These two will come. This is a repetition code. This is also cyclic code. Any doubts here? Are you following?
No, sir. Yes, sir.
What is that I'm saying? See, you are multiplying a of x into g of x, right? This is a cyclic code entire C, right? Now when I'm working with x power 7 minus 1, what are the degrees of the elements in C? What is the degrees? At most 6, right? Already g of x is degree 6. Then what is the degree of ax? Ax is a constant polynomial, right? So this is simply a times gx. What are the possibilities for a? 0 or 1, right? But what is the code corresponding to this? You can see that in the last class I explained, but I'll explain one more time. This is x minus 1 into this gx only. But therefore this is equal to 1 plus x square plus and so on plus x power 6. If you multiply these two, you will get this. Yeah, and so this is related to this code. And if I multiply with 0, then I'll get this. Is it okay now? Amya, is it okay?
Yes, sir.
Okay. Anyone has any doubts? So Suresh is clear?
Yes, sir.
Yeah, anyhow, last class we discussed. Okay. So in the last class, again, we done this part also. Generator polynomial G naught has to be not equal to 0. We proved that G naught equal to 0. Then we can multiply G naught equal to 0. Then what is going to happen? There is no constant there. So I can take x outside. X outside, right? When I take x outside, when I multiply x per n minus, that is x power n. X power n is 1 when I do modulo, right? That means now that is also a polynomial, right? So x power n minus 1 is nothing but x inverse. That is also belong to C. Okay, okay. So that is a problem because now that generator polynomial is a polynomial of the smallest degree, right? So that is a contraction. So this always not equal to 0. Small proposition, it will be useful as we move forward. Yeah. Now this is the thing I proved in the last class, right? The generator polynomial is of degree n minus k, then C is n minus k cyclic code, n comma k cyclic code. And if this one, then generator matrix for C is a k cross n matrix, it is going to be like this. So G of x, so I put first row as G naught up to Gn minus k and remaining are zeros, right? Then shift it. You know that x into G of x is a cyclic shift. So it will go like this, go like that, like that, like that. Finally, this x power k minus 1 into gx will get here. Now you know that cyclic code C actually, right? C is equal to what? Ax into gx. Ax into gx says that Ax degree is how much? Less than or equal to k minus 1, right? So, uh, so all these things are coming from these things only, right? What is Ax into gx, right? So here I wrote Ax into gx is a naught into gx, a1 into x into gx, ak minus 1, like this, right? So this is a product, right? So actually, ax into gx is actually linear combination of gx, xgx.
Sir, it should be strictly less than k minus 1, right? Yeah.
K minus 1 also allowed, right? See, n minus k plus k minus 1, how much?
Okay. Yeah.
Okay, basically what is it I want to say that these are the basis actually now. You know that, see, that is quite easy. Polynomial of degree k minus 1, what is the basis in general? Don't worry about gx. 1 x up to x power k minus 1. Right, but now these are divisible by gx also. Just multiply by them, right? So ax into gx are actually linear combination of x gx, x gx, x square gx, x power k minus 1 gx. Now convert these into a vectors, right? So this is a generator matrix. So every code word actually a linear combination of these. That's why it's a generator matrix. Yeah, very simple and very quite clean. Yeah, I feel so. Any questions? Yeah, please ask me if you have any questions, please. Good, nice. So now we know how to get the generator polynomial from generator matrix. So I done here entire everything. What is that I done is that these are actually the basis. For that, I proved that these are linearly independent. यहाँ prove किया था. These spans I proved here. You can understand it. Okay, not big deal. Now coming back to this polynomial again one more time. Okay, are you there? Are you ready? Okay. Concentrate now. So theory over, no problems. So n equal to 7, x power 7 minus 1 equal to 1 plus x into 1 plus x plus x cube. You know this, right? So now I want to look at the cyclic code corresponding to coming from this polynomial, right? What is it? What is the degree of this polynomial? 3. That is n minus 4. Okay. Now, what is a matrix, right? So this is first row as it is 1, 1, 0, 1. Second row multiplied by x, right? If I multiply it by x, it becomes x plus x square plus x power 4. So it will be like this. So is it clear? Generative matrix is clear. Yeah. Now I am giving you here more example, and field also I change it to F3 so that things will be much better for you. X power 4 minus 1 is equal to, you know that x minus 1 and x plus 1 into x square plus 1. And this also I explained you. X square plus 1 is irreducible polynomial over F3. It is because minus 1 is a non-quadratic restriction over F3, right? Over Z3. Okay. Now, how many factors will be there? How many cyclic codes will be there over F3 now? You know, 8, right? So first of all, I take I1, right? If I take 1, then degree of Gx is how much? This is my Gx. Degree is 0, right? Now, what is the code? Now, cyclic code. See, what is the dimensions, right? Hello? Am I going fast? See, G of x degree is n minus k. Degree of Gx is n minus k. Then cyclic code ka dimension is how much? N comma k. Because my generator matrix becomes k cross n, right? Okay. So degree 3 here, generator matrix size is 4 cross 7, right? This 7 is the length of the code word. This is n minus k, degree is n minus k, then G becomes k cross n matrix. Because first row correspond to Gx, second row corresponding to x into G, like that. N minus k. Yeah. Now can you tell me when it is 1, right? Then what is the cyclic code dimension?
What is one, you said?
G of x is 1. See, G of x is 1. So what is that I do? Okay, I'll construct it. Okay? What is generator matrix? Can you tell me? Okay,
Identity.
how I get, I'll tell you here. This is n minus k. G of x degree is n minus k. What is the generator matrix? How it coming? First row gx, second row x into g, third row x square into gx. How long I go? X
Okay.
minus 1 into gx. Now my gx is 1, right? I'll explain here itself. Okay, my gx is 1, right? So my gx is 1 means first is 1, right? Next x into 1, right? Now x square into 1, right? X cube into 1, bus, right? I will not go further. Okay, yeah. Now 1 means what? What is the polynomial? This is 1 means 1 plus 0x plus 0x square plus 0x cube. X into 1 means 0, 1, 0, 0. X square into 1 means x square into 1 means 0, 0, 1, 0. X cube into 1 means 0, 0, 0. Okay, am I clear? Mehak?
Yes, sir.
Yeah. So that is what I'm telling. So when X is, try to understand this. How do you get this? Can you help me while writing? Yeah, can you help me in writing? So X minus 1, right? What is the next one?
X into X minus 1.
X into X minus 1. Next one.
X square into X minus 1.
Yeah, I will not go further because whatever the polynomial you are multiplying degrees at most, so product should be at most degree 3, n minus k. Sorry, k minus 1. It's degrees. Yeah, okay. Anyway, what is the polynomial corresponding to this?
Minus
Constant
1.
is, yeah,
1.
1, 0, 0.
0,
Correct.
0.
Now it is simply cyclic shift of this, right? So you can easily see that. Yeah, cyclic shift of that. So this is this, right? These are already cyclic shifts. So any combination of this also cyclic shift. So it is forms a code, but you can replace minus 1 with 2 also if you want. When you are working with in F3, I can write this like this also. Not a problem. You are not happy with negative numbers, you can do this. Is it okay? Yeah. X plus 1, what happens? X plus 1 is also a factor, correct? When it is X plus 1, I hope it is clear. Right? When X square plus 1, why X square plus 1? That is also one polynomial, right? When X square plus 1, why this is like this? Can somebody help me?
Because the AX will be the constant 1 and X.
No, what is that equal to matrix लिख रहा है ना, इस तरफ में polynomials लिख रहा हूँ. So first row corresponds to X square plus what, second row corresponds to
X into X square plus 1.
yeah. Why I'm not going to another one more X square? Because polynomial degrees are at most 3 only. So X square plus 1 means 1, 0, 1, 0. This is X plus X cube, right? X plus X cube, X plus X cube, right? This much, right? So what are all cyclic code words now? So can you tell me how many code words will be there? C, can you tell me C? Somebody can tell me that how many code words will be there in this cyclic code?
4.
No. That's why I asked luckily. We are working in F3. Yeah. Can you tell me now?
9. 9.
No. Right. Okay. Good. We have 9. So try to write them and find the distances and all. But here much easier. So basically cyclotomic cosets, if you work more, then cyclotomic cosets will help you to figure out that what are the distances and those things also. Okay. Yeah. One more example, x square minus 1. Why x square minus 1 I wrote? Yeah. It is because x minus 1 into x plus 1, right? Product of those two. I hope these are all clear. Any questions? I wrote all the matrices to help you. Okay. Yeah. So this is a simple, little different one. Look at here that 6, right? What is the GCD of 6 and 2? 2. It is not 1. So the polynomial now x power 6 minus 1, right, is equal to x cube minus 1 into x cube plus 1. But what do you know about x cube plus 1?
It will be X cube minus 1.
Yeah, so these two are same. I'm getting square. So roots are repeated. You see that? Basically will not work in general, but I gave one more example of this type also to understand. Okay. But remember that generally we take n comma fq GCD1 will take, so that all are distinct, so no problems. But here our goal is understanding that later, but right now understanding that what are generating polynomials, what are generating matrices. So one more example I'm giving here. Okay. So x plus 1 is a factor of, so finally you know that this is x cube plus 1 is x plus 1 into x square plus x plus 1. So totally x power 6 minus 1 is this, right? So now what are the, thus we can list the generator polynomials for various cyclic codes of length 6. Total how many will be there? There are total how many irreducible factors are there for x power 6 minus 1? Though it is repeated, don't worry. You know that it is like number now 36, not 36. So let us say, yeah, 2 square into, yes, 36. 36 equal to 2 square into 3 square, correct? What is tau of 36? You remember? 2 plus 1 into 2 plus 1, correct? It is equal to 9. Similarly, here also we have 9, right? Yeah. So 1, x plus 1, x square plus 1. Why x square plus 1 I wrote here? It is because x plus 1 into x plus 1 is x square plus 2x plus 1, but that is x square plus 1 only. Yeah, like that I done all those. Okay. I'm explaining one after the another. You please let me know. The polynomial 1 clearly generates whole of f to power 6. The set of code words is all 64 vectors of length 6 over f2. Clearly, this code has no error detecting or correcting properties. Are you clear? Please respond. Hello? Are you clear or not clear?
Yes.
Yeah, okay. No use of this code because there are all words I took. Then how can I correct and detect, right? Nothing is possible, right? Yeah, okay. Now coming to 1 plus x. Now you see the beauty of all those things. 1 plus x, right? So you understand that why generator matrix is like this? This is 1 plus x. This is x into 1 plus x square into 1 plus x cube into 1 plus x. Yeah, x power 4 into 1 plus x. I will stop there. Why? I'm working in x6, right? So I can go up to polynomial of degree 5. Right? So now, what is the size of this matrix? Right? So my gx degree is 1. So then so my n is equal to 6. So n minus k is equal to 1. This is degree of gx. Degree of gx. Right? So now my k becomes 5. That you can see here. So this is 5 cross 6 matrix. So can you somebody tell me that how many code words will be there now? I'm working in I already wrote, sorry, 32 code words, right? So can you say something about this code? What are these 32 code words? Total how many code words how many words will be there in f to power 6?
64.
64. These are 32. Can you figure out that what are this code? So the dimension of f to power 6 is 6.
The sum should be even.
Sum should be even. Wonderful, right? So it is actually parity check code. Okay. So whenever I have this, or x minus 1 in particular, x minus 1 always divides x minus 1 always divides x power n minus 1. Na? It is always a divisor. Always a divisor. Okay. When I am working in F2, I wrote x plus 1, but do not write x minus 1 only, so that clarity will be there. I wrote x plus 1 because positive I can write instead of minus. Nothing. Okay. So always the generator matrix, so that is what I am told earlier. Parity check code is actually a cyclic code, right? Cyclic code. So generator polynomial is x plus or x minus. Yeah. Any questions? Suresh, is it okay?
Yes, sir.
So parity check code actually, you see, these are length 5, right? I'm adding some of the digits, okay? Length 5, length 5, length 5, right? Length 5. So one more added here. Now, if you take the linear combination, all the linear codes have, you know that, right? You know, we done one question. So U is a code word even weight, V is even weight, U plus V is also even weight, right? You know that if U plus V is even weight if and only both U and V have, both are even or both are odd. So that we done like this, right? Weight of U plus weight of V minus 2 times weight of the product, right? Dot product or something, right? Or weight of uh, component wise multiplication. Okay. Yeah. So this is exactly that. So I gave the explanation. So later you can check it. I wrote all the details carefully here. So can I proceed? Any questions? Okay. Now x square plus 1. A degree is 2, right? So now 2. So now here degree is now k value is 4. Yeah. Now here what is the capacity? Whether it can detect correct, that also I wrote. So I do not want to repeat. So now for this the matrix is like this, right? Now you try to check that. So I wrote all the 16 code words in this case. Why 16? The size is 4 cross 6, right? So now k value equal to 4. Therefore, dimension of the number of code words, cardinality of C equal to 2 power k, 2 power 4. 16 code words will be there, right? These 4 and any linear combination of this, right? That is exactly that I'll multiply A, B, C, D, correct? So A, B, C, D values are 0 R1, 0 R1, 0 R1, 0 R1. Okay. What is the meaning of 0, 1, 1, 1 multiplied to this? You know what is the multiply? I'll get it. Can you tell me?
Addition of second, third, and fourth row.
Yes, addition of all these 3 vectors, right? So 0 plus 0 plus 0 is 0, 1, 0, 0 is 1. This is 0. So it is 1. This is 0 and this is 1. Like that. Okay. Actually, that is a linear combination of them, right? But the coefficients are allowed are 0 and 1 only if I am working in F2. That is adding them. All possible additions of the vectors. Taking as it is or add. So we'll get total 16. These are the code words, right? So you can see that you take any non-zero code word here. Weight is 3. Weight is 3. Weight is 2. So weight is 2. There are no vectors of weight 1. So the weight of the code word is 2, right? Weight of the code is 2. So again, it can detect only, it cannot correct. So x cube plus 1, that is x plus 1 and x square plus x plus 1, then it is like, right? Now total how many code words will be there? Total 8 code words will be there, their combinations, right? Now again, weight has to be 2. Already no need to worry, because here itself, this row, here itself weight is 2. Now entire code ka weight also 2 only, cannot be 1. Yeah. So again, no use. Now look at this now. X plus 1, this is degree is 4. So degree is 4, right? Now, so k value becomes 2. So it is 2 plus 6. Now it is simple. Only 4 vectors will be there. 0 vector, these two and their sum. Correct? Now what is the least weight? You can see the least weight is, here length is 4, here weight is 4, here weight is 4. The least weight is 4. So that means it can detect up to 3 errors, correct 1 error. Yeah, so there are many code words of length 4, length 2, with the dimension 2. Yeah. So finally, I multiplied this one, right? X plus 1 into x square plus x plus 1 whole square. So it is entire this part. Generator matrix is only this, right? Now, what is the weight of this code? Can you tell me what is the weight of this code?
6.
6. Weight of this code is 6. So it can correct up to 2 errors, detect up to 5 errors. Okay. So till now everything fine. You have any doubts? I hope I explained with several examples. Anyone has any doubts? Okay. Now we'll go to parity check matrix, right? So we have generator matrix. So it comes from generator polynomial. The natural question asks, you can ask, is a generator parity check polynomial like that? Yes. See, g of x is generator polynomial for cyclic code C. Then we know that g of x divides x power n minus 1. So what happens? X power n minus 1 equal to gx into hx. Gx degree is n minus k. C has dimension k. So hx has degree k. Since hx divides x power n minus k, n minus 1, it is a generator polynomial for some cyclic code C dash of dimension n minus k. Now C perp has dimension n minus k. It is certainly would be convenient if h of x perp be generator polynomial for C perp, but there is no reason for this to be so. What's surprising is that generator polynomial C perp can be described in terms of h of x. Okay, so that is the reason h of x is called check polynomial or parity check polynomial of C. But bad luck is that it is not as it is hx. Okay, it is little bit C perp ka parity check polynomial is not hx. Okay, it is little bit variation. I'll tell you that. So to understand that one, you need to understand this theorem. Okay. But before that, I will give you the parity check matrix H of C. Okay. See, you can see here what is happening. Can you check something here? Matrix is written like this. Just tell me the observation so that I will help you later. What is happening? Are you able to see? Hello? No, I'm not asking anything. Can you observe here how the first row comes here?
So it is basically the h of x, but the uh, first column is the highest degree, the coefficient
Ah,
of the highest degree.
See, till now we are going in a constant first, like that we are going h0, h1, but now we are going in reverse order. That is what I want you to observe. For that, I'll tell you one thing. If, for example, my h of x equal to h0 plus h1x plus h2x square and so on plus hk x power k, right? Yeah. So can somebody help me that what is h of 1 by x, right? I'm just writing h0 plus h1 by x plus and so on hk by x power k. Is it clear? But it is no longer a polynomial. What I do now, I'll multiply with x power k, right? X power k into, now what happens? Can somebody help me? h0 into x power k plus h1 into x power k minus 1 and so on plus hk. Are you okay? Are you okay or not okay? Yeah, please respond.
Yes, so it's okay.
This is nothing. I put 1 by x and multiply by x power k. This polynomial is called reciprocal polynomial of hx. Okay. So what is that I'm doing? I'm multiplying by x power k, but x is replaced by 1 minus x. Now what is the degree of hx and x power k into h of 1 by x? Both have same degree. Only thing is that the quotients will be reversed. That's why it is reciprocal. We say. Yeah. Now this reciprocal polynomial is the generator polynomial for C perp, not h of x as it is. What is h of x? H of x is g of x into h of x equal to x power n minus 1. In particular, h of x equal to x power n minus 1 by gx. Yeah, but this is not the generator polynomial for C perp. It's reciprocal. That is, I'll take x power k into g of h of 1 by x. This is the generator polynomial for C perp, or parity check polynomial for C. Okay, and the generator, the matrix will count by this one. That is called the parity check matrix for the C. Right? These are the just told the facts, but we need to prove it. Yeah. So for that, just I'll want to tell you one small example. I will explain what is going on here, so that you will be understand everything. Right? For example, you take some polynomial like this, right? g0 plus g1x plus g2x square. Okay, and the h0 plus h1x plus h2x square. Right? But suppose I'm working in x power 4 minus 1, modulo x power 4 minus 1. Okay, right? Okay. So can you multiply and tell what is it going to happen? Can you multiply these two polynomials? Yes, please. What is the constant of?
G0, X0.
Not only that, one more, few more will
G2H2.
come. G2H2 also will come, right? Why G2H2 also came? You are correct. Why it came?
Yeah, take model for sorry
Ah,
X4. So
and yeah, right? Yeah, that is what I want to say. Okay. Let me now explain. Go to this. So be careful, understand this, and then so let us go here. Suppose we have polynomial a naught a1 an minus 1 and bx is b naught b1 up to bn minus 1. Right? Ax into bx is 0 modulo fq x by x power n minus. If and only ax is orthogonal vector. You know orthogonal vectors, right? This is I'm treating as a vector and work as a polynomial also, right? You are now familiar with that. When you say that two vectors are orthogonal, see now, so orthogonal means a naught into b naught plus a1 into b1 plus and so on, an minus and bn minus 1 is equal to 0.
0.
Correct. But what I am saying, not only these two are orthogonal, any cyclic shifts also orthogonal. So ax is orthogonal to the vector and every cyclic shift of this vector. Look at here what is happening. I'll explain you further. First understand the statement. Look at here. A0, look at this one first. AG, okay, anyhow, anyone is fine. So look at in all these cases, A0, A1, A6 are there, common, right? But now we have B6, B5, B0. Here what is happening, second row, okay? It is a cyclic shift, you see, B0, B6, B5, B1. Now again cyclic shift, cyclic shift, cyclic. Last one becomes A0, A5. So this is why these are coming. Okay. Now ax into bx equal to 0. Means I multiply these two polynomials and that product equal to 0, right? Yeah. Okay. Right. Okay. So somebody can tell me that this is quotient for what? So I'm proving for again, for example, as n equal to 7. That means I'm taking x power 7 minus 1 is equal to 0. I'm working modulo x power 7 minus 1. So this is a naught plus a1 x plus and so on plus a6 x power 6. This is b naught plus b1 x plus and so on plus b6 x power 6 multiply. So can you tell me what is the constant term here? Amya, are you here? Hello, Amya. Amya is missing. Who is this? Kaunil? Hello, Kaunil.
Hello, sir.
Yeah, Kaunil is what? Oh, you are Kaustubh?
Oh, my name is different here. I'm so sorry.
No, that's okay. Okay. Okay, so what is the constant term I'm asking? Suresh, can you tell?
yes, sir. A0 B0 and A4 B3
But
and
go
B
slowly, go slowly, go slowly. A0, you are telling A1 into something will happen.
no A1 and B5. Sorry,
So
B6
this, yeah. A2 into,
2 into B5,
very good. A3 into,
A3 into B4.
A, yeah.
A4 into B3,
B3. Yeah. A5 into
B2,
A6 into
B1.
B1. So look at these sums actually. You can see 1 plus 6 is 7. 2 plus 5 is 7. 3 plus 4 is 7. 4 plus 3 is 7. 5 plus 2 is 7. 6 plus 1 is 7. Right? So when they become 7, then I'll get. But 0, 0. So look at another way. If you add them and the quotient with modulus 7, they become 0. 7 means 0 only. Na? 0 plus 0 also 0. Right? So x power 7 when we get x power 7 means x power 0. Quotient when it become x power 0, when these are the things. Right? So in general, when you multiply, you do not do modulo, then only constant term is a0, b0. But when I do modulo x power 7 minus 1, this is the thing, right? So is it the second one? Mehak?
Yes, sir.
Yeah. So now this product is a 0 polynomial means constant term also 0. Constant term is given this. Now, can you tell me what is this actually in this product? मैं multiply किया. What is A0, A0, B6, A1, B5? Can you say somebody? What is this?
So if we multiply by x to one of the two A0 or B1, B0s,
No, no,
we'll
see,
get
do
this.
not tell like that. A0, B0, A1, B6, A6, B1 is what? It is what? In this product पे ये
It
product
is
करने के
constant.
बाद हाँ
It is constant.
हाँ it is constant. That means it is a constant term. Like that it is quotient of which one? This one. That is a question I'm asking.
X.
Is it for X? See, this is a polynomial of degree 6. It is a polynomial of degree 6. If I multiply again, I'll get a polynomial of degree 6 only. I will not go 7. Why? Because x power 7 is 1 I am taking. Right? Yeah, Suresh, can you tell me what is this A0, B6, A1, B5?
Sir, it is a quotient for x power 7.
7 or 6?
X
There is no
power,
x power 7. X power 7
yeah, so
means
x power, yeah, x power 6.
x power 6. Okay. If you multiply these two polynomials, A0 into B6 x power 6, I'll get x power 6. A1 into B5, I'll get x into x power 5, x power 6. Right? What is this one? A0, B5 and all?
X
Yeah,
power 5.
x power 5, right? So this is 6 degree quotient of x power 6, quotient of constant is a constant term, and quotient of x power 1, quotient of x power 2, quotient of x power 3, and up to quotient of x power 5, right? Yeah, okay, correct? Yeah, that's okay. Now look at here. So here B6, B5, B0, right? It's a cyclic shifts only. Why I wrote this term first? That is the reason. Okay, B6, B5, B0, it is a reciprocal polynomial ka coefficient. And these are uska cyclic shifts. Are you able to see them?
Yes, sir.
Yeah. So you know that G is a generating matrix for cyclic code. H is a generating sorry, parity check matrix. Then you know that G into H equal to 0, correct? So G into H transpose is equal to 0. You remember? G is K cross N. H is N minus K cross N. So H transpose, G into H transpose, it is equal to 0 matrix. So like that here, these two matrices, these two polynomials, if you multiply, I'll get 0. So this is not related to coding theory. How two polynomials multiplied here become 0? What is the meaning of 0? If they are 0, then this vector is orthogonal to orthogonal to this vector as well as its cyclic shifts. That is this theorem. Okay, good. So those are the things I'm taking. In H now I take these are the rows, right? So that is what this theorem says, right? So from that now it is clear. This is here I wrote completely. Okay. Now look at here. Now this is the generator parity check matrix for C. Yeah. And this is the, because of this now C perf is also cyclic. Because generator polynomial is cyclic, cyclic shift. Right? Yeah. Proof is given here. It is not complicated. But before that, do you have any questions? You understand how to compute parity check matrix now? So gx into hx equal to this. Take hx or x power n minus 1 by gx. उनका reciprocal कर लो. Then find the form the rows. Then it is generate parity check matrix H for C. Yeah. Now let me summarize everything one time. Let C be a cyclic code of, so this is summary, entire summary, whatever we done till now. I'm bringing one more time. Yeah. So if you follow this carefully, then all the last two classes, the last class and this class, everything will be clear. Let C be a cyclic code of length 1 over a finite field FQ. Each code word is associated to a polynomial among all non-zero polynomials obtained from C in this way. Let Gx be have smallest degree and monic also. By dividing by its highest coefficient, we assume that highest non-zero quotient of Gx is 1. The polynomial Gx is called generating polynomial for C. Then Gx is uniquely determined by C. First thing, Gx is a divisor of x power n minus. C is exactly the set of coefficients of the polynomials of the form Gx into Hx with degree of f is less than or equal to n minus 1 minus degree of g. If you write x power n minus 1 equal to gx into hx, okay, so then mx corresponds to element of C if and only hx into mx equal to 0, right? Why? Why? Because mx equal to, again, every code word is a multiple of gx. I know that hx into gx equal to 0, so that is this one. Earlier I told that the code words are in the null space. Now I am telling that code polynomials are orthogonal to hx modulo x power n minus. So this is the parity check matrix, and this is the generator matrix, right? These are the some of the problems, right? Yeah. So let me tell if you have any doubts in this, then I will give one or two examples so that much more better for you. Is it visible? I reduced so that everything at one place. Okay. Any questions? If there are no questions, then I try to do one small one or two problems, right? So that it will be beneficial to you. Here also some problems are there you can think of. Okay, so I'm giving this. I'm giving some small problem. We'll work out. Okay, so that how far you are clear. so that we can conclude the cyclic course, right? So let g of x equal to x power 6 plus x cube plus 1. Okay. Show that g of x divides x power 9 minus 1. Question number 1. Question number 2. Right. So then we have a cyclic code, right? So C is equal to, right, from I of x into gx, right? So degree of I of x is less than 3. Okay. So this is the cyclic code. With generator polynomial g of x, right? So find C. Okay. Now question number 3. So determine the generator matrix. Okay, what is the dimension of C? Small modification. X power 8 plus x power 6 plus x power. Okay. So I will change this. Yeah, you start doing the first few questions, right? Is x power 8 plus x power 6 plus x power 5 plus x cube plus x square plus 1 is a code word. Yeah, sixth one is that what is DRC? Yeah, is the question clear? Yeah, so can you say something now? Can we factor x cube minus x power 9 minus 1? So we are working in F2. Yeah. How do you write x cube minus 1? It is x cube minus 1 into, right, x power 6 plus x cube plus 1. Do you check? Are you able to see this? Hello? Mehak, are you there?
Yes, sir.
Yeah. You can check that multiply these two, will get this.
Yes, sir.
Yeah. So that is easy. You can check later. So this part is okay. Now, what is the degree of gx? Is equal to 6. Then what is the k value? Yeah, Suresh, what is the k value?
3.
K equal to 3. So can you tell me the dimension of the code now?
2 raised to 3. 8.
No, dimension
Sorry,
of the
K is 3.
yeah. So dimension of the code is k, right? So the dimension of the code is k, that is equal to 3, right? Yeah, okay. Now we'll try to compute C, right? So what is C equal to, right? So C equal to what is the tile take, right? A0 plus A1x plus A2x square, okay? Multiplied to my polynomial. What is the polynomial? 1 plus x cube plus x power 6, right? Right? And this is where A0, A1, A2 belong to F2. How many polynomials will come? 8 polynomials will come, right? Yeah. What is generative matrix? Okay. So one by one, you can understand here. So Ix is a polynomial, degree of Ix is less than, anything will work. Now total product become polynomials of degree 6 at most, 8 at most. But all of them are divisible by this. This is common, right? Yeah. Now, what is the parity check? What is the generative matrix for this? Can you tell me? What is the first row? This is the polynomial, right? Can you tell me the first
First
row?
row will be 0, 0, 1.
0, 0, constant 1 plus x square plus x cube. Yeah.
0, 0, 1.
X power 4 quotient, x power 5 quotient, 1. Total
And 0,
size,
0, 0.
remember the size of this matrix is
6 cross 9.
this is
Sorry, K 3 cross 9.
d cross 9.
Sorry,
Correct. 9, 9. D cross 9. It is 3 cross 9. Correct. So 9. But अभी तक कितना 1, 2, 3, 4, 5, 6, 7. Right? Why 7 came? Degree 6 है लेकिन क्यों 7 आ गया?
it is multiply with 1 vector. 1
No,
into 1 x.
that is not I am asking. Polynomial degree is 6 लेकिन क्यों 7 terms आ गया है?
because it contains one constant term.
Constant also, correct. Now 7 हो गया, so 0, 0 I'll put, right? Now I'll multiply with x, right? Then it is simply shift of this, right? I simply shift this. Now I write this entire thing, right? So 1, 0, 0, 1. I'm writing 1 here, okay? 0, 0, 1, 0. This is last 0 shifted here. Now again shift one more time, right? So 0, 0, 1, 0, 0, 1, 0, 0, 1. Are you followed? Yeah, right. Now you take the how many elements are there in C now, right? So cardinality of C is equal to 2 power 3, 8. So linear combination of these will come, and you once you know the word, then you know what are the polynomials also. Correct? Yes. So fine. So can you figure out what is the distance? So distance evaluate करने के लिए we need to write all the code words. Yeah. So let us write 3, 4, 5, 6, 7, 8, 9. Yeah, I'll write these as it is. It is little complicated. Do you work out later? Now I need to add these two, correct? So we'll just write 1. 1 plus 0 is 1. 1 plus 0, 1. Again 1. 1, 0, 1, 1, 0, 1, 1, 0. This is another one. Like the total we get 8. You can check all of them and look at the minimum weight. So you can see the distance of the code becomes 3 only. Are you okay? Are you clear?
Yes, sir.
Yes, sir.
I have not done all of them, but you need to do all of them. Here itself we have 3. And if you compute all of them, you will figure out that you cannot get, that is easy, see, without actually calculating. See, if I add these two, here 1, here 1, here 1 is coming, correct? More ones also coming, at least 3 to खा जाएगा. If I add these two, यहाँ 1, यहाँ 1, यहाँ 1 आएगा, correct? Minimum, right? If I add all the 3, first 3 में 1 आएगा, है ना? Are you able to see that? If I add all the 3, here 1 आएगा, यहाँ 1 आएगा, यहाँ 1 आएगा. So minimum weight is 3. So now if you add the vectors, now minimum weight cannot be less than 3. So already here it is 3. So distance of the code is 3 only, non-zero code words. Is the things clear?
Yes, sir.
Yeah. So you understand everything. This divides x power 7 minus 1. So then, so actually, what is actually happening is that these a0, a1, a2 are nothing but now we can as a polynomial here. Right? But here these are a0, a1, a2, 0, 1 or 2. So I'm multiplying to gx or xgx or x square gx. Yeah. So that is the overall business. So 8 coming from, and here binary strings of length 3, all are linked. Yeah. Okay. So now coming to this particular polynomial, you can check that actually it is a code word. The reason is that this x power 8 plus x power 6 plus x power 5 plus x power 5 plus x cube plus x square plus 1 is equal to, later you can check, it is equal to x square plus 1 into x power 6 plus x cube plus 1 only. So it is a multiple of this polynomial, right? So because of that, this is a code word. So this is a code word. What is a code word corresponding to this? Code word corresponding to this is 1, 0, 1, right? 1, 0, 1, 1, 0, 1. So this is the code word corresponding to this, and this belongs to C. Any questions? Okay, I'll delete this. Yeah, but are there any questions if you want to ask? Are you able to construct? Are you able to construct parity check matrix also for? Hmm? I will just give one more quick question so that you can tell things a little faster. No? So I take my polynomial as I'm working with x power 15 minus 1, right, over f2. My g of x equal to x plus 1 into x power 4 plus x plus 1. Okay. For the safe side, I will write this. Okay. So this is equal to x plus 1 into x square plus x plus 1 into x power 4 plus x cube plus 1 into x power 4 plus x plus 1 into x power 4 plus x cube plus x square plus x plus 1. Okay, all these are irreducible. Yeah? You can check that it is exactly product of this. So these two product is this my g of x, right? Yeah. So question one is that what is the dimension of this code? So can you tell me I of x degree is less than what? Can you say something?
Ten.
Hmm? 10,
10. 10.
10, correct. Because already 5 here, no? So maximum I can take 9. Yeah, correct. You are correct. 100%. Yeah. Then degree. So these are polynomials, so degree at most 9. But remember, there is a constant term. So what is the dimension of C?
10.
10, correct. Dimension of C is 10. Wonderful. Yeah. Okay. Nice. That is correct. Now forget about the G of X. I'll ask another question. So how many 15 comma 8 code words are found? Cyclic codes are there. How many? So my cyclic code is 15 by 8 means what is the degree of Gx?
7.
Oh, careful. Are you sure that it is 7? You may be correct. I'm just asking one more time. Yeah, 7, right? So 7, how do you get it? Which polynomials I have to multiply to get 7? That is a divisor of x power 15 minus 1, correct? So first, what is I'll multiply these two and this one. What is the degree of the polynomial? These three.
7.
These two and this one, right? These two and this one, 7. These two and this one, 7. So you are able to calculate how many cyclic codes are there of this dimension 15 comma 8 from this. Okay. I'm not telling all cyclic codes. When I give this thing also, you can tell now how many cyclic codes are there of with the dimension 15 8. There are 3 cyclic codes are there because there are 3 polynomials of degree 7 dividing it. Okay, how they come? Degree 3 here and any one of these degree 4 polynomials you can take and multiply. Yeah, so there are 3 are. Okay, so these are the questions I have, right? So try to find out for this polynomial, how do you find the generator polynomial? Sorry, parity check matrix for this. How do you, what is it you do? Just tell me that. What is h of x? Can you tell me? That is easy. You know that h of x into g of x equal to what? We forget. H of x into g of x is what? X power n minus 1 equal to h of x into g of x, right? Yeah, can you tell me h of x now? Be quick, I'll close now. This is what we have.
X cube minus 1.
X cube minus 1, correct? X cube minus 1, right? But in F2, x cube minus 1, x cube plus 1 are same. Do you agree?
Yes, sir.
Yeah. So now what is the reciprocal polynomial of this? That is x cube into h of 1 by x.
Same 1 plus x cube.
Same, na? Yeah, it is same. There is no difference in these two. So reciprocal polynomial and these two are same. Then you know that so this is the polynomial I'll take, right? And I'll construct the parity check matrix, right? So, but now I will go from, you can take this as a polynomial or you can take x cube plus 1. So this is better now. So now if you take this, then you would write directly constant first like that. If you take this one, then write highest term first like that. Okay. So if you take this one, then parity check. So forget about this now. Directly we will use this and I write. But be careful. Now x cube coefficient comes first, then 0, 0, 1. Right? Now 9, 9, right? So can you tell me the size of the matrix now?
6 cross 9.
6 cross 1. Okay, good. You understand, and you know that how to do. Multiply with x, multiply x square, x cube, and so on up to x power 3. Yeah, we'll get 6 x power 7. X power 5. X power 5 up to x power 5. Yeah. We'll get the parity check. So these are all easy. Yeah. So with that, I'll start today. Thanks.